Yeah, let's welcome back. So, previous lecture, I finished our lecture in this PPT slide. So that until I will explain the one-dimensional bar element. So that in today we are going to demonstrate the one-dimensional truss element either. However, but we are going to rotate this one-dimensional truss element so that into the two-dimensional spaces. That means that we do not put this one-dimensional truss element on the x-axis only, so that we can freely put our one-dimensional truss element in the two-dimensional spaces. So to drive the rotated or transformed truss element, we should check first the vector transformation. So let's start. So here, until last chapter, we put our one-dimensional truss element on the x-axis only, so that we only consider the x-axis. This is the original axis or global coordination system. However, we also can put our one-dimensional truss element in the local coordination system. This prime coordination is a local coordination system. So we should handle the matrix formation. That means that in this here, let's check about local truss stiffness matrix. I forgot. This is a local stiffness matrix of the one-dimensional truss element, and here this is a nodal point. However, this truss element position on the local coordination system, the variable can be expressed in the local coordination system. However, we should changing the coordination system. We should define this equation on the global coordination system. However, this truss element will be extended only x direction. However, in the global coordination point of view, so elongation occurred global x-axis and global y-axis both. So that means that we are going to change it. So maybe this displacement will be extended, looks like this. We should consider this y displacement. So maybe this also can be, we should consider the force in y direction. So and then that means that this 2x2 local coordination local stiffness matrices must become the 4x4 matrices. This today is our purpose is to derive the transformed local stiffness matrices from local coordination system to the global coordination system. To derive this transformed global stiffness matrix, we should first check the vector transformations. Here I prepared some simple vector, arbitrary vector u. This vector can be expressed in the both coordination. First, I define the global coordinations. This I and j is a unit vector in the global coordination system, and then I'm going to check some rotated coordination system or transformed coordination system, so that also this vector can be expressed in the other coordination system. Here, hat means that transformed coordination system, and then they should have another quantity. However, this vector is invariant property. I mean that these two vector say that same vectors. So, however, due to the due to the coordination system, they use a different element quantity in here. So, however, let's try the matrix transformation here. First, this is a unit vector of our global coordination system I, and then we can express this unit vector of the local coordination system, so that this I equal to the summation of this A vector and this B vector. A vector is some arbitrary vector in the other transformed coordination system. This B vector is some arbitrary vector can be expressed on the transformed coordination system, so that this A plus B equal to I. This is a simple matrix summation relationship. Here. And then, this coordination system rotated amount of the theta angles. That means that we can easily define the magnitude of the A is using the cosine relationship, so that is equal to the cosine theta. This is a projection of this unit vector, and then this B vector can be also projected in this direction, sine theta. This I is a unit vector. The magnitude is equal to 1, so that you can say that magnitude of the vector A is a cosine theta, and the magnitude of the vector B is equal to the sine theta. Here. And then we can easily say that the direction of the vector A is has this x-axis in the transformed coordination system, so that we can easily determine this vector A is has this magnitude of the A, and then we need some direction, so that in here we are going to use head unit vectors. So that we already know that magnitude of the vector A, and then this equal to look like this. And the B vector also we can know that the magnitude of the vector B, and then we know that the direction, this direction is a opposite direction of the unit vector of the J hat, so that we should add minus J hat, so that this is this unit vector A and B also can be expressed in the these vectors are expressed on their transformed coordination system. So anyway, this unit vector I is a summation of the vector A and B, so that means that cosine theta and I hat minus sine theta J hat. We can changing the unit vector of the I in the global coordination system into the rotated transformed coordination system. Looks like this. And then similar manner, we can also find out the relationship between the J unit vector in the global coordination system into the transformed coordination system. Same manner. J vector. This is a J vector. Is a summation of the A prime and B prime. So that A prime and B prime. Vector A prime is a projection of the J vectors to the this is the same angle of the theta and cosine theta, and then B prime is a sine theta J. However, this is a magnitude of the vector, and then J is a unit vector, so that we should take absolute value, so that this is equal to the cosine theta, this is equal to the sine theta, and then vector A is their magnitude, and then here direction is a j hat. This is a j hat directions, and then cosine theta j hat. B vector is their own magnitude, and the direction is this direction. That means that we can take I hat unit vector. The magnitude is a sine theta, this is a I hat. So in here, vector J is a summation of the sine theta I hat plus cosine theta J hat. So this same way we can obtain some relationship between the unit vectors in both coordination system. So we can say that our unit vector I in the global coordination system is a summation of the cosine theta I hat minus sine theta j hat, and then unit vector of the j is equal to the sine theta and I hat plus cosine theta j hat. So we can changing this unit vector I and j, we can replace the I and j equal to the transformed coordination system. This I can be take this one here, and this j take this value in here, so that after the reorganizing, the I hat is equal to the u cosine theta plus v sine theta plus j hat is equal to the minus u sine theta plus v cosine theta. These two vector is a same vector, arbitrary vector u. So that means that this must be equal to the u prime and I hat plus v prime j hat. That means that each component must be same. So we can obtain this relationship. U prime is equal to the u cosine theta v sine theta. V prime is equal to the minus u sine theta plus v cosine theta. So that we can changing the matrix form. So we obtain those kind of relationship. And then in this stage we obtain those kind of some 2x2 matrices. So this is a transformation matrices. So that I think that you guys already familiar with those kind of matrix. This matrix is some rotational inversion matrix of rotational matrices. Rotational matrix is a cosine minus sine and cosine. This is a rotational matrices. This is the inversion of the rotational matrices. So that in the FEM, we can say that the transformation matrices. So it is because that the rotational matrix is using those kind of matrices. However, our quantity, our vector is positioned, the relative coordination system is rotated amount of the theta. However, they feel the negative rotational direction, so that in here, so we obtain those kind of quantity on the transformation matrices. So anyway, so we obtain the single u and v prime is equal to the cosine, sine, minus sine and cosine and uv. So however, in the truss element we have 2 point. First u1 and second is u2. So and then this is some transformation matrices, so that we should consider the 2 nodal point here. However, in the truss element we are going to neglect displacement in the y direction. However, yeah, for the convenient to easily understand, we should consider the displacement in the y direction both. So yeah, this is some transformed or local coordination. Yeah, this is a global coordination system. So that between the two coordination system, they have those kind of relationship. Yeah, each has some rotational transformation. This vector also have some rotational relationship. Yeah, so that they combining in these two vector rotation form, so that we can say that the looks like this. We are going to say that this is a transformation matrices sometime. So that yeah, depending on your system, we are going to use only single transformation matrices or this total transformation matrices. So anyway, yeah, please do not confusing the notation of the t. So anyway, yeah, similar way we can say that the force vector, yeah, so although we are going to handle x-axis force only, however, we should consider the force in the y direction either, so that we can define the relationship between the forces vectors. In the two-dimensional spaces. Yeah, this also can be used the same manner. So okay, yeah. So yeah, using the previous derivative of the relationship between the local and global coordination system, actually, yeah, transformation of the coordination system, so that we obtain those kind of relationship. However, so we have only axis displacement in our local coordination system, so we are going to use only the displacement in the x-axis in the local coordination system. This displacement can be changing the looks like this. Yeah, so this displacement x-axis, so they can be decomposed the x-axis and y-axis in the global coordination system. So anyway, depending on your convenience, we can consider the only x-axis displacement in the local coordination system, or yeah, you can define the y-axis displacement in the local coordination system, and then you can changing the x and y both coordination system using the transformation matrices in the previous slide. So anyway, yeah, we have a stiffness equation in the local coordination or transform the coordination system. So our vector always expressed in the one-dimensional, or this vector must be expressed in the global coordination either, so that each local vector can be changing the looks like this, and then this become the k t u, and this part become the t f, and then yeah, finally we want to hope that total forces F equal to the KU. This is our final form, so that yeah, in the right hand side I want to put some of this T, I'm going to move to the left hand side, so that I'm going to take inversion matrices, and then K and T and U equal to F. So yeah, fortunately this inversion of the transformation matrix can be say that transpose matrix. This inversion is same to their transpose matrices, so that we can say that this part and then U equal to F, so that I'm not confusing. Yeah, I think that this is yeah, I have some mistype in our PPT slide, so that this is a final expression of the stiffness matrix equation in the global coordination systems. And then we can say that this is a global stiffness matrices, global local stiffness matrix in global coordination. And then the detail component, we should do the matrix multiplication. So this transpose matrices is a 4x4 matrices, and this is a 4x4 matrices. So that we should have a 4x4 K matrices. However, actually this K matrices is a 2x2 matrices. So that we should in this time we should expand this 2x2 matrices is a 4x4 matrices. Actually, in the one-dimensional cases, we neglected displacement in the y directions. However, for the convenient, we should consider the displacement in the v-axis direction, so that our local stiffness matrix can be expressed 1, -1, -1, and 1. However, remaining part is equal to 0. This is the same form of our local stiffness matrix in the only x-axis, so that this is some expanded matrix form. Or sometimes we can say that this is for the x-axis, v x second node, this is a y-axis, v2. So that after the matrix multiplication, we finally obtain those kind of result. So that in here C is a cosine and the S means that sine theta. So that this is, we can obtain those kind of relationship in here. So that every time I make some mistake. This is a force vector, and here this is a local stiffness matrices, and then responded displacement. So we don't need to x indexes. U means that displacement in x-axis in the global coordination. V means that displacement in y-axis in the global coordination system. So that here, this is a global local stiffness matrices in 4x4. So that this is for the only one single truss element. So that if you have some more element, we should assemble this local stiffness matrix into the global stiffness matrices. So that depending on your system, if you have a different number of elements, then you should assemble. Although I use some summation notations, however, this is a slightly different simple summation. So that I think you guys know that meaning of the assembly of the local stiffness matrix into the global stiffness matrix. So depending on your index of the node, you can have two ways, direct stiffness matrices or some other methods, so that you can use it. So after the assembled local stiffness matrices, you can obtain our solution of the displacement. So actually, let's back to the slide again. So then after the take this inversion, we can obtain some displacement value. So maybe it looks like this. So that, however, this is a displacement each nodal point in global coordination system. So yeah, so you should take transformation matrices again into the local coordination system. It is because that we want to know that element stress or element forces. So here, this is a element stiffness equation in our local coordination system. So to obtain the reaction process, we should put our calculated result in here, so that when you put, if we have obtained some value, we can finally obtain some forces value exactly. Depending on your system, this can become some reaction or other external forces. So anyway, so that to obtain this reaction force or external forces correctly, we should put these values in here. However, every time, already we obtained our displacement result in global coordination system. So some guys think this is it's the way easy to retransform in the local coordination system. However, we can already define, you can free define some forces vector or stress. Let's follow my explanation. In the element, we can define the stress. Stress is equal to the forces divided by cross-section area. So that I put one forces and nodal forces. I choose the second nodal forces in the local coordination system, and then the forces can be expressed looks like this. It is because that this part is a multiply summation these two vectors. So that I put some of these two vectors and looks like this. And here, let's check the it's uncomfortable to use displacement vectors in the local coordination system. So we can changing this local coordination system V to V cosine, sine, minus sine, sine, and then remaining 0. And then this part UV each node. So anyway, so and then however, we need only this U prime, U1 prime and U2 prime, so that we can neglect this part. So we can only use this. This is a 2 by 1, this is 2 by 4, and this is 4 by 1. The total result is 2 by 1 is equal same expression. We can say that you can use those kind of relationship, so that stress is some multiplication of some matrices with displacement vector, so that we can say that this is elastic matrices of the local coordination system. So that this is a stiffness matrix. In the previous slide, we already say that our Young's modulus and maybe 1 and minus 2 is this is a expression of the stress in the local coordination system. So so I also mistake in this slide. So that this is a stress expression. However, in if this one-dimensional truss element rotated, so we should use those kind of Young's modulus matrices. So I think that this is a simple matrix transformation problem, so that yeah, after the understanding the transformation coordination system, you can answer those kind of truss system. Yeah, this is a plain truss system, so that you can put the several element in our two-dimensional spaces. So that in the previous lecture, so that we only simply say that we can edit the one-dimensional cases. However, yeah, this is a rotated truss element. Yeah, this is also rotated truss element. So you can define the local stiffness matrices. Yeah, first for the first element. Yeah, this is the third element. This is a compared to L. This is a local stiffness matrix. You can say that you can define the local stiffness matrix of the each element. So that means that you can assemble this element to the global matrix system. So that please check some example problem. So that in the next lecture, I'm going to solve the more complex truss system, maybe bridge style system. So, and then, yeah, the matrix size, so that it's larger than our previous examples. So that I'm going to use a MATLAB. So let's check the next time of some examples. So that, yeah, similar manner, you can also define this one-dimensional truss element in the three-dimensional space. If you are familiar with vector transformation or some projection, vector quantity, so that you can easily determine our one-dimensional truss element in the three-dimensional spaces. So that let's define, so that if we have this is a displacement vector in the local coordination system. This is a one-dimensional cases. However, this is a displacement vectors in the global coordination system. Maybe that similarly they will have some relationship. Those kind of matrices we don't know yet. This is a transformation matrices. So that, let's define some vector. Let's define some arbitrary vector in the two different coordination system. First can be expressed in the local coordination system prime, or we can also define this vector in our some global coordination system. Using taking the product, that means that we can take some I prime or I hat. So, and then they have some orthogonally quantity. They are perpendicular each other, so that this two become equal to 0. So that, and then we don't know yet the relationship between the I, j, k with the I prime, so that we cannot say yet. And then anyway, u prime can be expressed some value with their global coordination quantity. So, however, we know that this is a I hat and this is a I, so that so this that projection means that they will return their magnitude is equal to the angles. This become the cosine theta, and then the quantity is equal to 1, so that we don't need to the other values in here anymore. So that this become we say that a cosine or directional cosine. So, and then every so that if we have another j, they have some angle, so we should use another subscription of j, so that this become the cosine theta y and cosine theta g, so that this become a cosine direction. So anyway, similarly, you can also define the v prime. So you have some j prime and I, and V prime, J prime, J, and W, J prime, and then K. So that, yeah, each has a different directional cosine. So that maybe theta Y or cosine theta, X, Y, Y, and theta Y, G. So that we can use a different directional cosine. So that anyway, all components can be defined in this way. However, yeah, in the one-dimensional truss element, we can only handle the x-axis displacement in the local coordination system. That can be expressed the displacement u prime in the looks like this in the global coordination system. So that our displacement vector of the one-dimensional truss element can be expressed looks like this. This can be also, we can say that transformation matrices. However, exact transformation matrices can be expressed exactly, looks like this. And in this stage, we neglected these four lines. So that anyway, so we obtained those kind of relationships. So that after using the sum, u prime, f prime also can be expressed the transpose matrices, and then this can be expressed, and then take matrix inversion. So that in here, so that in the previous slide we use not rectangular matrices. These have some rectangular shapes, not square matrices. However, you can say you can use this relationship. So anyway, this three component is can be expressed looks like this. Although they are they looks like very complex element. They have a very complex element. However, this is a very we can simply drive this local stiffness matrices. But just remember that they have a 1, 2, 3, 4, 5, 6, 6 by 6 local matrices size. So that, and also this is only for the one truss element. So if you have two element, for example, 1, 2, 3, so that will become let's guess how their global coordination system can be expressed 9 by 9 matrices. It is because that let's think about this one node has a 3 degree of freedom. I mean that they have a 3 component for the displacement vector. It is because that they will if they have some values in the displacement, so that we should check the whole component x, y, z component in the global coordination system. So each nodal point has a 3 degree of freedom. Total degree of freedom is 9. So that means that u1 v1 w1, u2 v2 w2, u3 v3 w3. So vector size is a 9 by 1. So that so local stiffness matrices, global stiffness matrices must become the 9 by 9. So anyway, this is a end of the derive the local stiffness matrices in the 2-dimensional or 3-dimensional spaces. So that next is so in the 2-dimensional or 3-dimensional spaces, if you designing some truss system, so there will become a very complex characteristics or stiffness equation. So however, when you're designing many element system, the global stiffness matrix will be has a 2n by 2n or 3n by 3n size. So that that takes a lot of time to assembled this element or to taking the inversion matrix, it will take more time. So to reduce the computational cost or our cost, so that we can use some geometrical symmetric characteristics, so that using the symmetric characteristic we can reduce the global steepest matrix size or system size itself, so that depending on the system we can use some reflective symmetric characteristics or mirror characteristics or some axial or cylindrical characteristics. However, today I'm going to skip the details, so then maybe next chapter I'm going to prepare some another lecture slide for the fourth chapter. I'm going to explain or prepare some very simple symmetric structures system. So anyway, so let's skip the details. So next thing I'm going to want to discuss about some displacement functions. I think that I slightly mentioned about some displacement function. However, in this slide, I'm going to explain more detail about the displacement function. Actually, it's a very simple concept. It is because that, in some single element system, we have a two nodal displacement variable. However, this displacement variable actually have some relationship depending on their coordination system. So that we can easily define the simple first order polynomial equation using, let's assume that displacement will have those kind of relationship. This coordination is x1, this coordination is x2. Depending on your coordination, this become x1 plus ax1 plus b, and then that must become u1, and then similarly, and the coordination x2, they must become the u2. So that this is a very simple relationship. However, some FEM has some limitation. Actually, on each nodal point, we can obtain the exact displacement variable. So although we do not define the exact total system, however, after the obtaining solution, we can say that the exact values of these displacement values. So, and then, however, can you say that the displacement of this solid structure on the center point? So that we don't know yet exact values on the center point of this truss system. However, let's back into your solid mechanics lecture. So in your last year, I think that you guys learned about the total displacement field. For example, when we learned about when we applied some forces on simple single element, I think that you guys learned about the total stresses each cross sections. It is I think that they will, although they have some similar value or same value, it is because that the displacement strain is a constant maybe. And strain is a constant. It is because that the derivative u is equal to the strain. So that means constant means that the displacement variable is a one-dimensional. This constant is going to say that have those kind of form. Do you agree with me? So after deriving the with respect to the x, that they become some c1. So this is a strain c1, so that we obtain the constant stress values in the simple truss system. So anyway, so also in our FEM simulation, we are going to use a simple one-dimensional polynomial displacement field However, yeah, although yeah, another cases, yeah, if we have a different cross-section area with respect to their coordination system, or in these stages, so we cannot say that the strain is equal to the constant whole region. So that at that time you should changing the displacement field. However, this is not our main focus. So that anyway, so that in our FEM simulation, we assume that our displacement field is a first order polynomial equation. This is our assumption. So anyway, so displacement function, next slide I'm going to say that here. So anyway, our displacement will be expressed first order polynomial equation, and then when we check in the very simple coordination system, maybe that will have some value in here, u1 and u2, x, so that depending on your displacement value, so that we can define this a1 and a2s exactly. However, we already know that in the position x1, the value is u1 x, and position x2, and then the u value is equal to the u2x. So that means that we have already two solutions, so that we can define the a1, a2 coefficient easily. So let's define the coefficient here. So then I'm going to set this is a origin point, so that x1 is equal to the 0 and x2 equal to the length of the truss element, so that we can say that this become the a1x plus a2, so that a1 plus a2x, so the x equal to 0, so that become a1, and when you put some the x is equal to L, so that a1 plus a2L. However, a1 is already defined u1x, so that you can put some the u1x. So anyway, a2 is equal to the L over the u2 minus u1x. So that in previous slide we defined this is a2x plus a1. So a2 and a1 can be expressed and looks like this. And here, so I want to say that actually displacement field in the FEM solution we obtained, we can know that exact values at each nodal point, so that I'm going to say that collect this value looks like this, here, so that I collect u1x and here, and then here u1 1 minus 1 over x plus u2x, where is the u2x? Here u2x, only single one, so that L over x, so that we can say that this is, we can changing this equation in the matrix form. So finally we obtained those kind of relationship. So in this stage we are going to say that these two element is a displacement function to express the total displacement in the single truss element. Actually we are going to obtain the two nodal point, exact nodal point values, so that if you guys know that exact displacement value at two nodal point, you can define the whole displacement field using this polynomial displacement function. This polynomial displacement function will have some simple linear relationship. If this point value is u2 and u1 and u2, so that the middle part is simply half values in here. So when you put some center point, x is equal to the 2 over L. That means that yeah, when you put some the 2 over L, final value is equal to the 2u1 minus u2. So yeah, maybe. So that we are going to define some displacement. Using those kind of displacement field, we can say that the displacement values in the inside our truss element. This is some assumptions of our FEM simulation. So yeah, also you can also define the more complex displacement function to explain the displacement values inside truss element. However, this simple displacement function is the most easiest way to explain the displacement values inside truss element. So that, yeah, so anyway, so we are going to say that this is a shape function. I think that this is a more general terms to say that these functions. So that I'm going in the next time I'm going to say that when I say the shape function, you can say that so this is a shape functions. So anyway, so that we can say that this component become L1 and this component L2, and then this is a U1 and U2. So yeah, this N1 is a function of the X. This is N2 is also function of the X. So that we can say that in the matrix notations. So yeah, this shape function has a very simple characteristics. So yeah, if you put some the X equal to 0, yeah, this big part first element N1 equal to 1, yeah, second element become to 0. However, at end point, yeah, this part become 0, and then yeah, second element become 1. So that they have one characteristics. Yeah, at each nodal point, each displacement function or shape function become the unit value. And then another second characteristics, yeah, the summation of the N1 and N2 always equal to 1, not 0, not is equal to 1. So that this is the second characteristics of the our shape functions in the FEM simulation. So and in here, so yeah, this is a Hooke's relationship in the solid structure system, especially one-dimensional truss element system. So the strain has those kind of relationship. Yeah, displacement variable will be derived by the X. So that this can be so the total so elongation is 1x, and then total elongation is a difference between the u1 and u2 axis, and the initial length equal to 1, so that the strain can be expressed and looks like this. So anyway, so yeah, in here let's back into our previous slide. Yeah, displacement can be expressed those kind of first order ordinary different polynomial equation. So and here we are going to obtain some strain fields, so that this constant becomes 0, and that this first order part remains those kind of value. This become a strain. So so anyway, so however, in the previous slide we are going to say that this is a 1 and 2 and u1 and u2. Those kind of vector form. It is because we are going to obtain the exact u1 and u2 values after the calculating those kind of linear algebra system. So similarly, I'm going to reorganize this value. So that u1 and u2. u1 is a multiplication 1 over L, and u2 is a multiplication plus, and here minus 1. This is a strain field. those kind of way in the previous slide. This I'm going to say that shape function, and each element of the shape function. However, in this stages, so that here, this n1 is a function of the x. However, u1 and u2 is not the function of the x. So that so that means that you are going to derive this u vector, so that this part does not affected by this derivative operator, so that this is some constant values, so that this does not changing in here. However, this part n1 and n2 are the function of the x, so that you should derive it by x, so that this part become the n1 and by x, so that we are going to say that this is become b1 and b2. And then next time I'm going to say that this matrices, so that to express the strain field, we are going to use some B matrices. B matrices is a derivative of the shape functions. So next time I'm going to say that every time I'm going to say that strain is a multiplication B matrices and the displacement vector. So that in these stages, although B is a vector, however, in the other coordination system, this B become some matrices. So that I'm going to usually say that B matrices. So anyway, please do not forget this B matrices. So anyway, so let's check the although we use a displacement function. However, let's check the first. Let's check our Galvani equation, equilibrium equation. Here, this is a Galvani equation. This Galvani equation is for the force equilibrium in the x and y and g axis. And then in here, if you have some body forces, so that we neglected body forces, or other types of the forces, so that so anyway, so to simply understanding, I only consider the one-dimensional spaces. So Hooke's law's equation, sigma x Young's modulus with the multiplication strain, and then equation looks like this. It is because the strain is a derivative displacement with respect by x, and then after then put some of this value in here. So the total, this del operator is also in here, and then this also, this is a strain equal to 0. To match this equation, we should consider the volume integration. So although all cross-section area always constant, so that we need some multiplication or cross-section. So however, if this value has a constant value as a function of the x, so that you don't need to consider this part. So anyway, our final equation is so also Young's modulus is a constant or as a function of the x, so that we don't need to consider that anymore. So this equation become looks like this. However, in the previous slide, we defined our displacement is a first order polynomial equation, and then also we defined those kind of relationship or n1 and n2 relationship. So here looks like this. This n1 and n2 is a first function of the x with the first polynomial equation, and then we also define strain, first derivative x, so that we obtain those kind of B matrices. So anyway, however, in these stages, our governing equation second order derivative with respect to the x, so that yeah, in this stage, yeah, after the take one more time, yeah, this become equal to 0. It is because the all value is a constant value. This is not a function of the x anymore. So that in this stages, so that yeah, all equations can be equal to 0. That means that yeah, we are going to obtain some exact values in here, maybe yeah, 0 or 0.001, those kind of values. However, yeah, actually this equation always can become 0. It is big, yeah, it is big, yeah, so that yeah, those kind of displacement function we cannot obtain our exact solution. Yeah, so anyway, so we need some way to, we cannot use those kind of second order derivative equation anymore, so that we are going to changing our Carbony equations. Yeah, it is because that yeah, our simple one-dimensional simulation or model always matched this equilibrium equation. However, yeah, we are going to use a more complex system. Yeah, sometimes we have a different cross-section area at that time. Yeah, displacement variable can be defined other second order polynomial equation or first order polynomial equation. At the time we don't need to worry about those kind of equation. However, in the FEM simulation we are going to use a very simple element, for example, yeah, same cross-section area or other very simple cases. At the time, yeah, always match those kind of relationships, so that we cannot define some unique values. Yeah, actually you can put some any infinity values in here. Yeah, so anyway, yeah, second derivative is always equal to 0, so that yeah, we cannot obtain the unique values in here. So yeah, we want to use a very simple displacement function to define our displacement values in by FEM simulation. However, yeah, next way is defined more complex displacement function. However, it's not it will increase computational cost. So yeah, next way is changing this equilibrium equations. So yeah, this is a way how to changing our equation. Yeah, first way is changing this our equilibrium equation to the force energy equation. Yeah, I think that we already discussed about the total potential approach, minimum approach method, so that we are going to use this approach method again, so that yeah, total energy is a summation of the internal energy and the work done by external forces. So the external energy is some solid structure experienced some deformation. That solid structure can store some internal energy, looks like a spring. So that this part is strongly related to the deformation of the solid structure. This omega is to deform the solid structure. Yeah, we should apply some external forces into the solid structure, so that this the total energy is a simple summation of the internal energy and external forces, work done by external forces. So that we can easily define our internal energy is a force is equal to the displacement. Yeah, force is a stress and cross-section, and then cross-section area is when we choose the very infinitesimal small element, so that this is a cross-section area, and then the displacement is equal to the d, so that yeah, if we have some length, and then yeah, the increment is equal to the their initial length equal to the strain, so that we can say that those kind of equation. This is internal energy. So that this internal energy must be summed in the whole total volume element. So our in the previous slide, our infinitesimal equation can be integrated first in the x-axis, in the total strain fields, and then this small internal energy must be summed with respect to the whole total volume system. So anyway, we are going to use a very simple one-dimensional truss system. They have a same cross-section area, so that we can say that this is a very simple two integration can be changing the simple cross-section, constant cross-section values, and then this become the it is because that they will have those kind of relationship. So that we are going to take half the energies in here, so that, and then remaining integration is x. And then similarly, we can also define the external forces. If they have some body forces in the whole domain, we can multiply the displacement and total forces with in the total volume. And then if some solid structure have some forces on the surfaces only, we can take we can sum the total forces by surfaces forces, so that they integrate in the only surfaces. And then the remaining part, we have some point, nodal point, those kind of way, so that we can simply sum the nodal forces, and then with the multiplication of displacement. This is a work. The unit is always equal to work, maybe joule. So that external forces can be expressed looks like this, and then this part is internal energy. This part is point nodal forces, external forces by point, and this part surfaces, this part volume, external force. So, and also you can changing this part is a matrix form, and then but normally we can neglect, we don't have any surfaces forces in our truss element, and then we don't have any body forces term, so that we can say that these two parts become to 0, and then we are going to consider the only simple nodal forces in here, F1 or F2, so that this part can be remained in here. So, and then this part can be also expressed looks like this. We have two nodal forces in here, and also we have two displacement value in here. 2 by 1 by 2, 2 by 1, that becomes scalar value, 1 by 1 scalar values. And here, so in the previous slide, maybe this internal energy can be expressed the stress and strain, and then maybe, am I right? This is internal energy U. However, let's back into our previous slide. In previous slide, strain is a derivative derivative of displacement function by x. So then in previous slide, I say that U is expressed looks like this, and then we should take derivative operation. This part become the n1, n2, but u1 and u2 is not the function of the axis, so that this part become B matrix. I already mentioned that. So that this strain is a multiplication B matrices and displacement value at nodal points. And then also stress. Stress is a multiplication and Young's modulus and strain again. So we already know that this strain can become a B matrices with multiplication of the displacement vectors, so that Young's modulus, in these stages we have one-dimensional cases, so we can say that E itself, however, depend when you consider the other dimensional cases, these Young's modulus must be changing to some other matrices, stiffness matrices. So however, we just think about this is a scalar matrices. So in here, in here we should take some transpose matrices. It is because that this here this equation here 2 by 1 by 2 by 1 sorry 1 by 2, this is 2 by 1. So sorry, so that to match the matrix order, so that final solution must be equal to the scalar value, some values, so that this is correct to take some inversion. It is because that you can easily say that in this stage stress and strain is a constant value in here. However, let's consider the two-dimensional cases. We have 3 components in here. Similarly, with some Young's modulus matrices in here, and then this strain, this is a shear strain, so that they have some expanded vector form equation, so that to match those kind of relationships, this is energy, so this becomes a scalar value, so that 3 by 1 and 3 by 1, so that without the transpose operator, that cannot become a scalar value, so that this become the 1 by 3 matrix, 3 vectors, so that we need the transposes operator in here. So anyway, so after the taking transpose operator, this stress become Young's modulus and multiplication and strain, and then take transpose matrices, so that you go to the first part, middle B is a middle part, D become Young's modulus with transpose. However, this is a Young's modulus itself. This is a scalar value in here. So anyway, we obtained those kind of equation in here. You can put some of this equation in here. So anyway, we defined total energy of the truss system. So next approach is find the minimization value. To find out the minimum values in total potential energy approach method, we should take some inversion. Total potential must be equal to 0 to become each value equal to 0. Each component must be equal to 0. So that those kind of way we can take derivative equation in here. In here, we have u1 and u2 transpose. I already transpose equation f1, f2 in here. This become 1, this become 0, and then remaining equal to f1. And similarly, you can find the f2. So however, in this part, similarly, this u1 and u2 and b matrices. So in previous slide, we can say that b1 and b2, and then this is a Young's modulus, and then b1 and b2 and u1 and u2. So in here we have a 2u1 and u1. This is a second order equation with respect to the u1 displacement element, so that we can obtain those kind of relationship. Actually, b1 is equal to the 1 over L, and b2 is equal to the minus 1 over L. After the put this value in here, you can obtain those kind of equation in here. So, and then similarly, we obtain those kind of equation in here. Finally, we can obtain the same form, our local stiffness equation. So this is a way to obtain our local stiffness equation. Sorry, I think we have some this typo in here, so maybe this part, sorry, yeah, I think that this become a equal to 1. So yeah, those kind of way we can obtain those kind of equation finally. However, yeah, similarly, another way, yeah, this is a u, this is a u. Yeah, actually this part is some value. Yeah, we can say that this is a square value of the u2x, so that if you want to derive this equation, yeah, we don't have enough spaces, so that this pi is can be expressed u square. So anyway, yeah, we have some values in here, yeah, to derive this total potential energy with respect to the u function, so that we can obtain the 1/2 equation u. This is a very simple way to obtain those kinds of equation. This is another method. However, yeah, I don't think it's, so in here, yeah, remaining part here, and then yeah, we have in previous slide we overlap and they cancel out each other, so we can obtain those kind of equation very simply. However, first try to each component, calculated each component separately, so that, and then combining these two equations in the single matrix form. Yeah, this is a more easiest way to understand the derivative, our Stephen's equation by potential and minimum approach method. So yeah, this is a next slide is some way. So yeah, in the previous slide, our total potential energy equation looks like this, and then the derivative with respect to the displacement is equal to equation looks like this, and then yeah, this part, yeah, this u we can separate, we can check this equation separately. Yeah, this equal to have some form ku equal to f. That means that this part is a local stiffness matrices in here, so we can say that, yeah. And then yeah, this a is some integration with respect to some surfaces, so that this integration is for the volume integration. So this equation, more general equations of the stiffness matrices in here. So this is a really general equation. Yeah, in the previous slide we defined our displacement function as a first order polynomial equation. However, yeah, if you want to put some those kind of second order polynomial equation at that time, this is a1 2x a2, in this here, maybe the shape function can be expressed n1 and n2, u1 and u2. However, if you have a 3 unknown component, that become n1, n2, n3, and u1, u2, u3 maybe. So that at that time you can easily define the b1 and b2, b3 derivative shape functions, I, so that we can obtain those kind of B matrices easily, so that you can use these B matrices anyway. And then if we have a two-dimensional elastic stiffness matrices, you can also use it. So this is a more general equation. However, in the truss element, we are going to use those kind of equation to define the local stiffness matrices in here. So this is some simple examples, so that if we have our displacement result, this is an exact solution of our displacement equation. If we use only single element, we obtain exactly these two values are same, compared to the exact solution. However, we assume that this this element has a simple one-dimensional polynomial relationship, so that in the middle point just follow the linear interpolation relationship. So to reduce the error, this part has a large error, but each nodal point has a 0 error. This is an error. So that to reduce this kind of error, so that the simplest way, we have use one more element. This is a U2, this and that point, this become U3. U1 and U2, U3 has a 0 errors. However, between the two node point, they have a simple linear interpolation relationship. They have some error. However, in this time, that those errors are reduced compared to the single element cases. So I think that I hope that I want to reduce this error, so that the next way is using the more element. Those kind of way we can have a very small errors compared to our exact solution. This is approach the good solution to obtain the good solution using the FEM simulation techniques. So, and then those kind of way, in the inside element we obtain the constant strain value. So that if you use a single element, we obtain the simple stress, constant stress value. However, exact solution has some variation, displacement value. I'm not sure that they will have some polynomial equation. So using your solid mechanics background, so that if you guys use a two element, so that element stress have a two different value. It looks like this. The error will be reduced. However, I think that it's a big errors, and so that to reduce those kinds of error, the simplest way is increase number of element your system. So this is just some example. Next is next weight residual method. This is another way to derive our FEM equation. So stiffness equation. So compared to the energy potential approach method, this method is more straightforward. It is because that they going to use same forms of the partial difference equation. However, maybe I think that to define the global stiffness equation in the plane stress or plane strain, two-dimensional cases, we are going to use this weight residual method. So however, I do not prepare the details about the weight residual method. So next time I'm going to introduce the weight residual method. So I think it's more convenient to derive our stiffness equation compared to the potential energy approach method. So actually we have several method: collocation method, subdomain method, and least square method, and Galerkin method. I think that next time I'm going to introduce what is the Galerkin method. So however, today I'm going to skip the details. So this is a flow chart how to use our FEM technique in the solid structure, so that all things first define system, and then define the element type. This is first we should know that what kind of local stiffness matrix or equation, and then to discretize our system very finely, and then computed stiffness matrix, local stiffness matrices, and then assembled this local stiffness matrix into the global stiffness matrices. And then we should take several time depending on your number of the element, and after obtaining the global frequency equation, and then before solving this part you should apply some boundary condition first, and then finally we can obtain the solution those kind of simple way, and then we obtain some solution displacement. And however, in the solid mechanical engineer more want to know that the stress or forces compared to the displacement or strain, so that you should calculate or compute element forces and stresses. This is a post-processing that, so that after the engineer or other scientist can check the result, and then plot the result which you want, so that this is a process how to using our FEM simulation. This is a summary. Today we learned about how to make truss equations, and then we also defined our truss one-dimensional truss equation to the two-dimensional spaces using the vector transformations. So I think that using those kind of methods, we can use a very complex truss element. Maybe next time we are going to designing and check those kind displacement and strain or forces in those kind of truss bridges. So and then I think that those same manner you can also derive our one-dimensional truss element in the three-dimensional spaces. So and then today we are going to learn about another way to derive the stiffness matrices in using the potential energy approach method. So that maybe next time we are going to discuss about more detail about the symmetric conditions and then Galerkin residual method, so another way to derive the stiffness equations. So this is the end of today's lecture. So if you have any question, please ask me freely anytime and you want. So thank you for hearing. 오늘 강의 들어주시느라 고생하셨고요. 원래는 조금 더 이어서 더 연결을 하려고 했는데 얘기를 하다 보니까 좀 길어져서 오늘 이번 주 4주차 강의는 여기서 마치도록 하겠습니다. 이미 업로드 해드린 콤솔 예제도 한번 풀어보시고요. 콤솔 예제 제가 아마 원디멘셔널 트러스 엘리먼트의 1차원에서도 예제를 한번 드렸습니다. 그래서 한번 책에 있는 예제랑 손으로 풀어보신 거랑 콤솔로 풀어보신 거, 그 다음에 제가 매트랩도 한번 어떻게 프로시저 하는지도 준비를 해드렸으니까 한번 이번 주에는 이제 원디멘셔널 스페이스에 대해서 다 이제 충분히 이해를 해보시고요. 아마 다음 시간에는 제가 이제 이 원디 트러스를 투디멘셔널에다 배치를 했을 때 솔루션을 어떻게 얻는지에 대해서 먼저 손으로 푸는 거랑 매트랩으로 이제 좀, 왜냐면 계산량이 많기 때문에 매트랩을 그냥 갖고 온 거고요. 그런 프로시저를 거쳐서 어떻게 하는지를 보여드릴 거고요. 그걸 이제 여러분들이 콤솔로 한번 또 같이 솔루션이 똑같이 나오는지를 한번 비교를 해보시는 과정을 다음 주에 갖도록 하겠습니다. 고생하셨고요. 다음 주에 더 건강한 모습으로 뵐 수 있었으면 좋겠습니다. 수고하셨습니다.